title of the section. And it's one of the bigger ones, and it's one, I'm going to give you the exact wording that comes up a lot on free response questions. That and intermediate value theorem. The two are, if you just use the exact words, it just makes your life easier. Okay? So we're going to talk about that in a second. What it does, it just tells you that at some point on an interval, the average rate of change has to equal the instantaneous rate of change. That's what it says. It doesn't show you how to do it. Doesn't show you anything else. It's just an existent theorem, like the one you didn't like before. Do you remember that? It's just another existent. A lot of it, it's not going to show you how to do it. It doesn't tell you, like, if it happens multiple times. It just says, if this and this happen, then I guarantee you that at some point the derivative is equal to the average rate of change on the interval. Okay? That's all it says. That's it. Nothing more, nothing less. Okay? So let's get into it. Can you guys see this? So this one, like, I try to put a lot into words just because, you know, it's words and stuff, and just kind of understanding what's happening. So I'm going to do a couple examples and just kind of go through this. Just ask me some questions. The mean-value theorem connects the average rate of change of a function over an interval with the instantaneous rate of change of the same function at a point within the same interval. The theorem says that somewhere between points A and B, here's a nice pretty little picture, somewhere between these 2 points, A and B, on the curve, there's at least one tangent line parallel to the secant line connecting the two endpoints. So if I found the average rate of change between A and B, that would be the slope of this secant line. If this is a continuous function, it's differentiable on the entire thing, then at one point, there's a tangent line that's going to be parallel to it. Okay? That's what it says. There's some point C that's equal to the average rate of change between points A and B. If you got some continuous function at every point on the closed interval and differentiable at every point on the open interval, then there exists some point C in that interval such that f prime of C is equal to the average. Okay, the average rate of change, or the slope of the secant line. Those are the words. That's what you need to know. Okay? If you have all of that in your explanation, you'll get all the points in the free response. You need, because continuous on the closed interval and differentiable at every point on the open interval, then there exists some point C on that interval where the derivative value at that point C is equal to the average rate of change. That's the important part. Okay, that's what's going to come up. So make a flashcard with that exactly. Again, this theorem only tells us that a number C exists, not how to find it. But here's an example how to find it. You got some function x squared plus 2x minus 8 on the interval 0 to 2. I find my two endpoints, that's 0, negative 8, and then 2, 0. If I find the slope between the two endpoints, or the average rate of change on the interval, or the slope of the secant line, I get 4. If I take the derivative of x squared plus 2x minus 8, I get 2x plus 2. If I wanted to know the x value, where that derivative was equal to the average rate of change, I can set those two things equal to each other. Does that make sense, Chris? And then sort of back solve for the x. So I take the derivative function, 2x plus 2, set it equal to that average rate of change on the interval, which was 4. And then what I can do then is solve for the x value, or in this case I put it a c there, that'll give me that derivative value. So at 1, I'll have a derivative value of 4. And if I plugged it back into my derivative, yeah, 2 times 1 plus 2, yeah, that is 4. How are we feeling, Jessica? Okay, good. Any exciting news?
Yeah, someone actually had the wrong number.
Oh! I was not expecting that today. All right.
That is...
Okay. Since f of x is continuous on the closed interval 0, 2 and differentiable on the open interval, the mean value theorem by MVT, I've just guaranteed myself a point C where the derivative value is equal to the slope of the secant line. The tangent line to this function, x squared plus 2x minus 8, at x equals 1, has a slope value of 4, which just happens to be parallel to the secant line joining those two endpoints. Okay, does that make sense, you guys? Now, here's why you need differentiable. You need both. You need continuous, because otherwise you can can just start and end. You know what I'm saying? You need a closed interval because you need the endpoints. And you don't even need to state, you should have both words here just so they're said, but if it's differentiable, then that you guarantee yourself the continuous. Okay? So as long as that's the big word there, differentiable on the open interval. So here's x squared. X squared. I want to know what the average rate of changes of the x squared function on the interval -1 to 1. What's the average rate of change of the x squared function on the interval -1 to 1? It's 0. If you find your 2 points, this is the point -1, 1. This is the point 1, 1. y2 minus y1, well that's already 0. 1 minus a -1 would be 2. So I got an average rate of change of 0 on this interval. Yeah, and here's that secant line. There it is. See it? Do you see it right there? Okay. Mean value theorem states with this closed interval continuous function, this is also differentiable on the open interval. There's at least one point where that instantaneous is equal to the average. Well, I can take that 0, which was the average, and I set it equal to the derivative of x squared, which is what, Estella? 2x. And can I solve for an x value that'll give me that as a derivative value? Yeah, you just divide both sides by 2, and x equals 0. Okay? Bam, we're done. We actually could solve it in this case. Well, what about my old buddy, absolute value of x on the interval -1 to 1? What is the average rate of change on the interval -1 to 1? Yeah.
Well, can't you not do it because it's not differential?
Bam. Yeah. But here's where it falls apart, you know. And the same thing on the same interval, -1 to 1, the average rate of change is 0. Yes? The average rate of change is 0 again, okay? But where on this interval is the derivative equal to 0? Never. This is all -1, and this is 1. It never equals 0. And it doesn't fail mean value theorem. It's not part of the test. You know, it first has to be continuous on the closed interval, differentiable on the open interval in order to guarantee it. If it's not differentiable, there's no guarantee. There could be. I mean, there's plenty of functions where that'll happen. You know what I'm saying? Even though it doesn't pass, you know, it isn't differentiable. You could still have a value, but what mean value theorem is a guarantee, no matter what, at least 1. It could be more as well, but at least 1. Yeah.
You said it has to be differentiable on the open interval?
Yeah.
That means it has to be differentiable on the whole thing. Is that
Yeah.
right?
And what they're saying, like on the open interval, is because, like, you know, to check the derivative. How do you check the derivative at a point? Well, you got to check to the left and to the right, make sure those values are the same. So you can't really check the endpoint. You know what I'm saying? You need to be continuous. You need that endpoint. But if you think about it, it's tough to be like, here's your endpoint. So you're coming off of it. So it's not like you have a corner. You know what I'm saying? You're just coming off. You know what I'm saying? Does that make sense? And if you're indifferential on the open interval, meaning you can use that endpoint to check this point right there. You can get to the left of it and check. Does that make sense, you guys? Okay. So otherwise, like, you can't check. But it's like, it doesn't really matter. It's like, you can only come off an endpoint, you know? Okay. Good. So any other questions on that? But again, it's just a guarantee theorem, just like our good friend, intermediate value theorem. You don't remember what the heck that one said. This is MVT. And by MVT, there's a point where the instantaneous rate of change equals the average rate of change. What the heck was IVT, intermediate value theorem? What was the goal of that one?